And I'm going to send out the URL so that people who are, hopefully some people are waiting for the URL and not just go like, woohoo, no class. No, they didn't say no class. They only said face-to-face interaction is suspended. Classes are still going. All right. So I'm going to refresh, making sure that I send the correct link. Okay, so this is still active. Very good. And there's a way to get the link to it. I just have to find out from where. Get shareable link. There we go. And go back here. There we go. So we got that. And I'll start that myself over here. And there's the chat on the side. There we go. And I can peel this out and see if I can resize that. No, doesn't like that. Okay. This can get a little awkward because in order to interact with the chat, well, I don't have to type in the chat, so I can just overlap it like this and then do the recording like this. Yep, so it's still recording good. All right. So I think we're all set up. The mic is good, going, and OBS is recording, and there's also me in the picture now. So what we'll do today is to continue our discussion of instructions, how opcodes relate to microcode, and how the microcode eventually control the various components of the processor to get the job done. Okay. So what I'll do is I'm going to go with what your lab activity needs to do tonight. Okay, so we'll go ahead and take a look at that. So tonight we'll be talking about simple branching and code analysis. Okay, that's what the lab is going to be about. Okay, so I'm going to do a preview. In other words, the access code is available at the end of the stream. All right. So right here it says the increment instruction increments the value of a register, but it does not affect the flags. This makes the instruction more useful because in many situations, the objective is to add 1 to a counter or address. In many situations, the objective is to add 1 to a counter or address, but it's also important to preserve the flags from a previous compare instruction. Using the opcode table or the assembler, find out the binary opcode of the following instruction. Increment C. Okay, so the most important part here is to find out which opcode and how do we encode the bit pattern for register C. So that's not any more difficult than this. In fact, this is slightly easier compared to the stuff that we have talked about before. So I'm going to go on to the second question. So the second question says the JMPI instruction, or the jump immediate instruction, has an immediate operand. In other words, it takes a constant. Okay, you just tell it which location is the next location to execute. When we get to the JMPI instruction, then it will continue execution wherever you specify. But the point is, I is static. In other words, once the code is assembled using the assembler, it does not change during runtime. Okay? So every time it executes this instruction, it will continue execution at whatever instruction that is specified. And it also makes use of the concept of a label. A unconditional branch instruction is useful to handle the cases when the conditional branch is the unconditional branch is useful to handle the case when the conditional branch does not match, does not branch, then we need to go somewhere else. Okay, so we have to talk about branching instructions today, including unconditional branch and conditional branches. Okay, these are really useful because this is how we make control structure. Conditional statements, loops, those are all implemented using conditional branches and unconditional branches. So I'm just going to scan through, all the questions. This way, I can structure the lecture today to make sure that we go over everything. All right. So the third one is talking about a logging capability. It's built into Logisim, so this is great. Okay, Logisim by itself has a logging capability, so we can log it inside Logisim. But I'll also talk about a separate technique to log everything to a file, so we can use an analyzer to analyze the actual result of something. So that's another thing. And the last question has a particular program, and I need you to kind of run it through. So to find out which one, from the log, you have to kind of come to the conclusion of which conditional branch instruction will give you the most occurrences. Okay, so you're not going to be able to answer the question during the lecture, okay? But I will talk about the concepts that you need to understand in order to answer those questions, okay? So that's why I presented the lab first, just so that I know what is the scope of today's lecture, and also for you guys to start to relate those concepts as I talk about the concepts. So do we have any questions at this point? No questions? All right. So if there are no questions, we'll get started with the conditional branch instructions. So the first thing I need to do is to start up Logisim. So let me start up Logisim. And I'm just looking for the easiest way to do it. 1870. There we go. So here's Logisim. And we'll open up the processor. There we go. All right, so we have one of the tools that we need in order to start today's lecture. The other one is the assembler. Okay, so if you have not done so, you might want to bookmark the assembler, because the assembler is very useful when we do our homework assignments. So we go to the assembler, which is in the shared folder under processors, and it is over here. There we go. All right. So we're going to start with a program that illustrates how the JMP instruction works. Okay? So we go to source, and this time I have a JMPI instruction. How come it's view only? Because it's using the wrong account, so I'm going to switch back to my school account. There we go. So this time I can actually change it. There we go. So we'll specify a JMPI instruction. If you don't mind counting locations yourselves, okay, you can always count the locations and say, I want to branch to location 8 or something like that. So I'm going to use that as an example. Okay, we are branching to location 8. So now we have to space out stuff in between. Okay, and one way to space out stuff is to kind of count. This instruction takes up 2 bytes. Okay, and you can use // to as comment. Okay, everything from // all the way to the end of a line is considered comment. I borrowed that from C++. So this would be byte 0 and byte 1. This is going to be byte 2. And all we need is a whole bunch of halt instructions, no-op instructions, and stuff like that. So that's 3, 4, 5, 6, 7, and here's location 8. So at location 8, I want to do something that's kind of fun. Let's go back to location 0. So we have an infinite loop, but it's not a very tight. Well, it's kind of tight, but not as tight as it possibly can be. But it will illustrate the point of a branch instruction. So before we do this, let me just well, actually, how do we know that the second JMPI instruction is actually at location 8? Well, remember, this is what the assembler does. So when you go to the Assemble tab will give you the information that I need. So it shows that the last instruction, which is JMPI 0 on row 8 of the spreadsheet, is in fact starting at location 08. So I should have a pretty, I should have an infinite loop program at this point. It will never get to the halt instruction, okay? So are we good so far? All right. So I'm going to load this program into RAM. So that means I go to the RAM file and go to download as CSV, save the file, and I usually just save it to the temp folder, and I'll call this JMPI because that's what it's illustrating. Okay. Switch to Logisim, go to the RAM portion, right click, and we say load image, temp jmpi.csv. Kind of double check that we got the instructions here. Okay, so we got everything. So now we want to run the program. Now, obviously, running this program is not really exactly fun because it's an infinite loop. It will never get to the halt instruction. So what is the point? Well, the point is I want to control T through the whole thing so that you can see how the JMPI instruction work. Okay, because the more I do this, the more you do it yourselves, the more you understand the processor architecture. And that's the whole point of this class, is to understand the processor architecture. Okay? All right. So we do a control T, but before we do that, then we go to over here, because we kind of want to focus on, okay, we are fetching, right? So the first control T, the first rising edge, is going to grab whatever the program counter is pointing to, which is location 00. It has a content of 40 in hexadecimal, and it's going to store that into the instruction register, which is what you see kind of at the top of the design. Okay? So when I type Control T, you should expect the instruction register to update to 40. Okay? So Control T right now. Sure enough, okay, it is now updated to 40 because that's the content at location 00, which is what the program counter is currently pointing to. Are we good so far? Okay. So when I do a Control T again, it's going to be a falling edge. The falling edge only affects the microcode pointer. So in this case, because the select going into the multiplexer feeding to the microcode pointer is selecting 1, so that means we are only incrementing. So we're expecting the microcode pointer to just increment to 001. Nothing too fancy over here. So Control T, and sure enough, microcode pointer is now at 001. None of the other registers got impacted or affected by this. Okay? But because location 001 has a different content in ROM, so that means the control signals to all the multiplexers and everything else can potentially change. So you can see right now the program counter is going to increment when I do a Control T. We talked about this already, okay, in the previous class. So the program counter is going to auto increment, which we will be able to see when I scroll over here and just scroll up a little bit here. Okay, so when I type another Control T, you should see the PC to increment from 00 to 01. And the reason why we want to auto increment is because the content at location 01, in location 00 is already used. Okay, so there's no need to point to that same location again. Okay, so here we go, Control T. Sure enough, the program counter is now at 01. Okay, right here. Now, if I type Control T again, which is going to be a falling edge, this time the microcode pointer is going to be affected. But the way the microcode pointer is going to be affected this time is you can see the select is selecting input 0 from the multiplexer. So this means we are going to combine the 40 in the instruction register with the constant of 0 just feeding into bit 0 to bit 3 of the splitter, so that the microcode pointer will now become 400. Okay? So in this case, in this particular processor, it's easy to tell because all we are doing is padding an extra 0 to the right-hand side of the opcode itself. That becomes the starting point of the microcode slices for the instruction that I want to execute. So do we have any questions at this point? Nope. OK. I'm just going to check with my YouTube thing. Absolutely no activity. Suspiciously. OK, well, if that is the case, we can move on, right? OK, so ControlT. So you can expect the microcode pointer to change to 400, which means it's going to address 400 in ROM. OK, so we type under the ControlT, like so. So now we are looking at the bit pattern coming out of the ROM through the D port. This is how we implement the JMPI instruction. So the question is, how do we do that? Okay, that's the question. So we're going to go through the same analysis that we did on last Thursday as well as this Tuesday. Okay, so we're going to go through the same type of reasoning. So we look for things that are enabled. The first thing we notice is, the program counter is enabled. In other words, we are going to change the program counter. The question is, how are we changing the program counter? So whenever you see a register is going to be changed, the next question is, how are we changing it? Okay? So, well, we just look at the D port of the program counter, and it's coming out of a multiplexer. So with the multiplexer, you look at the select. It is light green, which means we're using input 1 in this case. This is input 1. Okay? So without actually going through a very detailed discussion, I'm just going to highlight and then we go to where it goes. Okay? So it goes from here. This one is light green, which means we're selecting this one. And ultimately, what you will find out is, it's coming out of the D port of RAM. Okay? And we know that RAM is involved in this operation because RAM cell is a 1. RAM is selected. Okay? So if RAM is selected, you got a few extra questions to ask. 1, which location? 2, are we reading or writing? Okay, so those are all the questions that you kind of have to ask as follow-up questions. So now that we know RAM is selected, well, let's go check out load first. Okay, are we reading or writing? Load is a 1, which means we are reading from RAM. Okay, but which location are we reading from? The location that we are reading from is coming from the A port. So the A port goes all the way back to this multiplexer. This multiplexer has ADDR mux or address mux, specifying a 1. So that means input 1 of this multiplexer is going to the A port of RAM. So now we have to track down, where is this coming from? And if you track it down, it goes like, it's going back to the program counter. So this looks really kind of awkward because we are using the program counter as a pointer to point to a location. Whatever is at that location, we are going to use it to update the program counter itself. Sounds like a loop, but it's not a loop. Okay? The only reason why it is not quote-unquote a loop is because the program counter is only sensitive, it's only updating on the rising edge clock. So that's why we don't have a problem. It doesn't keep changing like crazy. Okay? So this is what we can expect is the program counter is going to change to whatever content is now at location 01. What is at location 01? 08. So the program counter is going to update to 08 on the next rising edge. Do we have any questions about this? That's great. I got, you guys cannot see it, but I see 2 people saying all good here and no questions. Excellent. Okay. So ControlT, and you can see that the program counter is now at 08. What is the job of the program counter? It points to the location of where the next opcode is coming from. Okay? So what this is saying is we are now going to execute is whatever is at location 08, right? Okay, so if I type ControlT one more time, the ROM is going to switch to the next location, which is going to be 2 followed by all zeros. So we talked about this already. All that is going to do is to reset the microcode pointer back to 0, 0, 0, which is where the fetch is coming from. Okay? So I type ControlT, and you can see how the microcode pointer is now going back to 0, 0, 0, which means it is now ready to go to whatever location the program counter is pointing to, fetch, and then decode, and then execute again. Okay? Except this time it's going to be going to location 8. What happened to location 2, 3, 4, 5, 6, and 7? That skipped. Okay? So what I specify in those locations really did not matter at all. Okay? They're just filling up the space. Okay? So if I ControlT again, ControlT, 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 you can see we are going back to location 400 in ROM because that's another JMPI instruction. Except this time, the next location, or location 09, has 00, which is telling JMPI to go back to location 00. So now we can see that there's a loop. So do we have any questions about how an unconditional branch instruction works? Question? Go ahead.
So the program counter counts to the location of the instruction of the jump, and that's different from an instruction pointer.
Okay, so that's a very good question. The question is, to summarize the question, is the program counter the same as the instruction pointer?
Right.
They are the same.
Okay.
So it's a terminology thing. With Intel, they like to call it the IP or the instruction pointer. In most other architectures, it is called the program counter. So it's just a nomenclature thing. You know, some companies want to stick with a particular name, and other companies want to use a slightly different name. Okay. But they really mean the same thing.
Counter kind of has me hung up because I use counter.
It is a counter because normally, unless you have a jump instruction, it just keeps incrementing.
Right.
So it is a counter of sorts. You know, when it is not branching. It is
for unconditional jumps.
For any type of branches, you know, it's not going to increment.
Okay.
Except unless, you know, the branch does not happen. All right. So now we are ready. Now that we have understood what an unconditional branch instruction works, now we get to probably one of the most difficult instructions to understand of this entire architecture. It is called a conditional branch. So a conditional branch, as the name implies, is conditional. Okay? So now the question is, conditional to what? Okay? Because we haven't really talked about the Boolean type. We don't have any variables. So condition to what? The flags. Okay? So everything that we understood about flags is now coming back because the conditional branch instructions would look at the flags and say, hey, if the carry flag is a 1, I'm going to branch to whatever the next byte is telling me to branch to. If not, I'm not branching. I'm just going to continue with whatever is next to that particular instruction. Okay? So let me change the program. Okay? So if anyone has questions, do not hesitate to ask. And I have to be careful because there's about 10 to 15 second lag between real time and when people actually see it. So I have to kind of give myself a 15-second lag or delay before I move on to a new topic once I ask, are there any questions? So I'm counting down right now. Okay, apparently there are no questions. Very good. So this is kind of interesting because this is kind of like the first time I have to wait 15 seconds after I ask, are there any questions? Okay, so we switch back to, wrong browser. This browser is actually where what I see. You cannot see the other side. You can only see the side where the screen capture is. But the other side is the chat. I'm looking at the chat right now. Okay, so we'll go ahead and go back to our assembler. One person says, I think this process will be easier once it's 100% online. That actually is not the case, because when it's 100% online, it simply means every single time I ask, are there any questions, I will have a little stopwatch on the other side or timer on the other side to time like 15 seconds before I actually moving on. Okay. All right, so we're going to change this program a little bit, and so that we can experiment a little bit with conditional branch instructions. There's not really a whole lot that I need to do differently. So we'll go to, where's my source window? Oh, there we go. There we go. One person says, can I repeat the student's question? So, the question was basically, is the IP or instruction pointer and the program counter the same thing? Because you got some exposure to the x86 architecture, and the answer is yes. Okay. All right, so let's go ahead and change this program a little bit, and we'll change this to a conditional branch instruction with a JCI instruction. Does everybody feel like counting bytes so that you can say, okay, where we want to go to is at location 8, or do you think it's better to use just labels to label those locations? I think labels are easier, okay? So we'll just use a label here and say, when C is 1, okay? And if you do this, the assembler will come back and say, it is unresolved, okay? When C is 1, okay, it's unresolved, okay? It changes everything to lowercase, so which is normal because I don't have a label. So all I need to do is to put a label maybe around here, and we say when C is 1, colon, and now the assembler is going to resolve the reference, and everything is good again. Okay, so we'll put a halt instruction here, and we're going to have another halt instruction here. So this is useful because now we have 2 halt instructions. Depending on which halt instruction is where we stop, we can now tell, did it happen correctly or not? Okay, did we actually branch correctly or not? Another issue that we might have with this particular program is, well, but the carry flag is going to be cleared because everything is cleared to begin with. So there's no way we can actually test this program, whether it branches conditionally or not. So we'll address that issue a little bit later, but right now we are just going to say, okay, the carry flag is by default cleared, which means it should not branch, which also means the halt instruction on row 2 is where we stop. Okay, are we good so far? So we want to track this down and see how that happens. So we go to RAM file, go to File, Download, CSV, and this time it is JCI. Okay. Go back to the processor, do a Control-R, reset everything, because this time we are changing the program too, so it's okay to do a Control-R. Right-click, load image, and this time we are loading JCI.csv. So we got our program, okay? And you can see the JCI instruction has a different opcode. This is all coming from the opcodes table, okay? So the opcode itself really doesn't really mean a single thing. All it is, oh, by the way, this binary bit pattern is JCI. So 4440, the bit pattern itself has no intrinsic meaning other than go ahead and look up at 440 in ROM this time to find out how to do it. Okay, that's basically the bottom line of that. Okay, so we'll do some Control-T's, okay, until we get to location 440. So Control-T, 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 Control-T. So now we are at location 440, and we want to find out, what is the difference between the JCI instruction and the JMPI instruction? Okay, how come one is conditional in terms of branching and the other one is not? So the first thing we do is we check out the program counter. When we check out the program counter, you go like, oh, okay, just like last time, the program counter is enabled. In other words, on the next rising edge, it's gonna change. Okay, so that part is already known. But now the question is, what makes this conditional? In other words, which part of the processor says, hey, take a look at the carry flag and use the value of the carry flag to do something differently, depending on whether it's a 0 or 1. Okay, so that's what we want to discover this time. So now we have to look at the flags register, because all the flags are stored in the flags register. The flags register has only 5 bits. Okay, you can see here it only has 5 bits because we have the carry flag, we have the Z flag, the 0 flag, we have the sign flag, the overflow flag, and the L flag. Those are the 5 flags that we have. The carry flag is bit 0 of the flags register. Okay, so we want to focus on bit 0. Now, if I ask you, what is the value of bit 0, what do you think it is? Even without any understanding of hexadecimal digits. Looks like it's got to be 0 because it looks like every single bit is a 0 this time, right? Okay, so, but how do we isolate just bit 0 from the flags register? So now we look at the Q port of the flags register, which is the output, okay? And that goes to, now this part, this output pin is only here for debugging purposes, so by itself, not very useful. It goes into a multiplexer, exactly. So it goes into this multiplexer, and every bit goes into a different input of that multiplexer. Yes. Yeah, because I got some extra input pins, so I go like, okay, we'll type both of those to zeros. But the more important part is PieceInMarks, okay? PieceInMarks is called PieceInMarks because it is controlling a multiplexer, and that the output of this multiplexer controls yet another multiplexer. So it's multiplexer control squared, okay? Yeah, we'll see it, we'll see. Okay, so we look at this so PieceInMarks comes directly from the ROM, okay? So it is 0, 0, 0 as a 3-bit pattern. So that means we are selecting input 0 to become the output, okay? So that means we are taking this input so that it becomes the output. Is that okay? So the output is now PieceInMarks, but PieceInMarks is now a 0. So what does that do to our PC, the program counter, this guy over here? So PieceInc is directly controlled by the ROM, okay? So it's a 0 this time. AddressMarks is a 1, which is also directly controlled by the ROM. So you can see how I lied. I just lied. I lied, yes. So I lied flawlessly because if I didn't say that I lied, nobody would have known that I lied. So PieceInc is not coming straight from the ROM. PieceInc is the output of a second multiplexer. So with this multiplexer, it is taking the output of the first multiplexer, and and then the select, which is PieceInMarks, becomes PieceInc. It controls whether to increment or not. Okay?
So,
go ahead.
Question.
Yeah.
So I'm looking at the output from the first multiplexer and the second multiplexer. Why is it not just one multiplexer and then having, why is it not just the second multiplexer?
Okay, that's a very good question. So the question is, how come we need 2 multiplexers? How come we don't just take the output of the first multiplexer and make it PieceInc? Is that kind of the summary of your question? Okay. So the conditional branch instruction, for the conditional branch instruction, you are 100% correct that we do not need to do it that way. Okay? But if you look at the constants, you can see how input 5 of the first multiplexer is a 0, but it is a 1 from the second multiplexer. So we'll talk about why those are slightly different for the last 3 bits. Okay? But for the conditional branch instruction, you're absolutely correct. It does not really matter. I could have taken PieceInMarks as if it is PieceInc, and it would still work the same way, more or less. Okay? So now we go back to the program counter. And then we ask, how are we updating the program counter? Well, first of all, it comes from this multiplexer. So you can see how PieceInk and PieceMarks actually serve different roles. Okay? Even though a lot of times they are the same, they do serve different roles. PieceMarks controls the multiplexer that is feeding the program counter. PieceInk, on the other hand, is contributing to whether we should increment the program counter or not. Okay? Now there are some cases where PieceInk is actually needed, but this time it is not, because addressMux is already doing a good job. Because addressMux, which is the same line as this one, is now used to specify, yep, this needs to be a 1, and we are going to increment. So the end result of this is we are incrementing the program counter, and therefore we are skipping the byte that specifies where we are supposed to go. And then the program counter just get incremented again to location 02, and we are not branching.
I'm not seeing how this is skipping, because isn't this just the same as when it increments normally?
It basically treats the JCI instruction as if it is a no op, but with 2 bytes. Because it's incrementing the program counter again. The first increment comes from location 001 of the ROM. This is the second increment, so that we are now skipping both bytes of the JCI instruction, which in effect is saying, oh, just continue with whatever is after the JCI instruction. Do not branch, as the JCI instruction says. Questions? Okay. All right. So if I do a ControlT at this point, I think most people will just say, okay, the program counter is just going to go from 01 to 02, because it's selecting 0, which is coming from the adder. The adder has a carry in of 1, because addressMux is one of the things that I use to OR in order to determine are we incrementing or not. AddressMux is a 1 because I'm using the program counter to specify the address of RAM, but in this case, RAM is actually not used. Well, actually, okay, I take it back. RAM is actually used, but this time, even though it is addressed, it is selected, and it is in the read mode, the data coming out of it is going to La La Land, because the multiplexer input, where the output of RAM is connected to, is not selected. Is that okay? So this is how we make the decision. Are we incrementing, or are we going to where location 01 is pointing to? Are we good so far? So now we're at a place where we can say, okay, we can just go ahead and execute this instruction as it is now, which means the program counter increments to 02, and then we go to location 02 to execute that halt instruction, and then everything stops. So I think that is not exactly very exciting. We already know that in this case it's going to go to location 02. So why don't we go to the flags register and ask, what if I change the flags register so that bit 0 is now a 1? Nope, we don't have to reset a single thing, because I have not yet commit the change. So I can actually tweak the flags register at this point, so that I can play out the second scenario of what if the carry flag is a 1. Is that okay? Yes?
You mean just manually doing it?
Yeah, I'm just manually doing it. Yep.
Yeah.
Okay, so let's go ahead and do it this way. So I go to the flags register and say, let's change it to 01. Okay? I just need the least significant bit, or bit 0, to be a 1, because that's our carry flag. So how is that going to change everything? So you look at the multiplexers. Well, what used to be a 0 are now 1s. PieceMarks is a 1, and PieceInk is also a 1. Then you go like, oh, PieceInk is a 1, that's no good, because we don't really want to increment, because this time we wanted to use whatever the program counter is pointing to in RAM to update the program counter.
But now PieceMarks is selecting the other input.
Exactly. So right here, okay, let me scroll to the right place. So right here you can see this is changed. It used to be a 0, now it is a 1. So now it's using input 1 of the multiplexer to update the program counter. So now we go to input 1 of the multiplexer, and it's coming out of another multiplexer. And the select of this one is PieceInMarks and not RO0EN. But in this case, since RO0EN is a 0, so when you do when you perform this AND, it will give you a 1 as the output. This is the select. It is selecting input 1. And when you track down this wire, it is coming out of the D port of RAM. That is how we make a decision of, are we going to skip the JCI instruction, or are we going to go to where the JCI instruction is telling us to go to? Yeah. So if it doesn't make sense right away, okay, you can kind of try to reason it out a little bit, step by step again. And I can tell you the focus is PieceInMarks. Okay, PieceInMarks is the decision-making, key. Okay, so to understand why we have two multiplexers here, and the difference is sometimes we want PieceInMarks to be a 0, and we want PieceInc to be a 1. There are a few cases where we want that. So PieceInMarks and PieceInc are not the same. This gives us the case. Yeah. There are a few cases where we need one to be a 1, the other one to be a 0. Yep. But not in this case. In this case, yes, we could have used just PieceInc or PieceInMarks as if it is just PieceInc. Yep. Okay. So if we follow through this one, okay, then we know the program counter will update to 0A, because we can actually probe the wire going into port D of PC, and you can see how it is 0A already. So on the rising edge, we know the program counter will become 0A, which means the halt instruction at location 0A will be the halt instruction that we go to. Are we doing okay so far with this? Okay. So now the question is, okay, now that we can understand, how a particular instruction, gets the job done, by analyzing all the multiplexers, the demultiplexers, the decoders, and so on and so forth. The question is, how do we debug a program? Okay, if you are to write a program and you want to say, did I get here? Or when I get here, do I have the right values, and so on and so forth? How do we keep track of all that stuff? That's the next question, okay? So what I'll do is I'm going to reset the processor. The clock is already low, so that's good. There is a way to reset the processor, but without resetting RAM. Because if you click a button that is next to the reset line, I think it's up here somewhere. There we go. So this reset button only resets the processor without resetting RAM. So this way you don't have to reload your program into RAM. You can keep using the same program while you're just resetting the processor to start from the beginning again. Okay? Kind of a handy feature. So you click on this one, and you can see how the processor, and what you can do is you can look at the microcode pointer as well as the program counter. Both of those are now reset to 0. Okay, so that means the processor is starting from the beginning, but the RAM content is maintained. So it can be handy. Okay, it can save you a little bit of time, when you don't have to reload content into RAM. Are we still okay so far? Okay. So the next thing I want to show is really just what are the debugging tools that we have with this type of architecture. Okay. So the easiest one to use, okay, not the most super useful one, but it's easy to set up, is you can go to Simulate, and then you go to Logging. Okay, so once you get to this logging screen, you can now select what you want to log. Okay, all of the things on the right-hand side are things that you can log. Now you can see certain things have the same name because one is referring to a register and the other one is referring to the output pin. Okay, that's the only difference. For instance, flags has two because this is the output pin called flags. This is the register also called flags. So you have to look at the icon to find out which one is which one. Okay, they are the same anyway. Okay, so no matter which one you use, it's going to be the same in this case. So let's just say that we want to keep track of the program counter. It's always good to keep track of the program counter when you're trying to debug a program, because the program counter tells you where is that instruction. Okay, it doesn't tell you what the instruction is, but you can look it up. If you know the program counter, you can always go to the assembler, go to the assemble tab and ask, okay, what is here? What was the original source code? So that's not the issue. The issue is, do you know where you are in the execution of the program? So the program counter is really important in this case. Okay? If you want to log something else, you can always log some of the registers. So registers A, B, C, or D can also be logged. This program doesn't change anything, so it's not going to be particularly exciting to log register A, B, C, or D, but you can if you want to. So I'm going to log one of these. You can also log the memory. So if you go to RAM, okay, right here, so RAM can be logged, but when you log RAM, you have to kind of double click this, and you can specify which location in RAM you want to log. Now, this program doesn't change anything in RAM, so we're not too concerned about locations in RAM. We're not going to log anything in RAM. Okay? Later on in class, okay, when we deal with the stack, calling and returning and stuff like that, then we have to do logging of RAM, because there'll be massive changing of RAM. Yes?
Do you have to specify the individual RAM block you're looking to log?
Yes, you do. I think there's no way to log all of them by default. You have to select the ones that you want to log. So the question is, to echo the question, to repeat the question was, if I need to log multiple locations in RAM, do I need to specify individual locations, or can I select a block and select an entire block? The answer, I think, is you can only select individual bytes. So if you want to log the last 2 bytes, then you have to say log location 255 and location 254. Okay? I believe there's no other way to do it, but if you find it, let me know. Now, if you say, wait, we don't need that, you can always just remove it. Okay? So for now, for this particular program, we are only going to log the program counter and register C. Now, when you log, the default is everything is going to be logged in base 2, which may or may not be what you want. Okay? Because base 2 means it's binary, which means it's going to be a long bit pattern. So you might want to change it. So if we go to PC, you can say, I'm going to change the radix. Okay, I'm going to change the base. So it's in base 10 now. Now it is in base 16. Okay? The flags register makes sense to log it in binary because you want to separate the individual bits in that case. But for the program counter, yeah, most of the time I think you just want the hexadecimal version of it and not the binary version of it. So you can control which base you want to use, base 2, base 10, or base 16. Okay, let's see what else we can log. You can also log the clock. Okay, now if you log the clock, there'll be a lot of stuff going on. Okay, if that is your intent, that's fine. Okay, it's not a problem. On the other hand, most of the time, I'm not going to log the clock because it will create a new log entry if one of the things that it is watching has a state change. That's how the log works. Okay, are we good so far? Okay, all right. So now we can go to the table. So when you log, there are 2 options to log. One is to use a table, which means it is only viewable when you have Logisim up and running. Okay? It's quick, but it doesn't give you the ability to send it to a file for further analysis. So that may or may not be a cool thing to do. You can always go to a file. Okay? So when you specify a file, you just have to specify where you want that log file to go. So I'm just going to say log.tsv. I use TSV because it is a tab-separated value file, as opposed to a CSV, which is a comma-separated file. This is going to be tab-separated. Okay, so you can click Save. And file output is enabled. Okay, so if you click it, it becomes disabled. Okay, so the button specifies the action, and the text on top of the button specifies the current state. So the current state is it is enabled. If you click the button, it will be disabled. Okay, so are we good so far with this? Yep.
If you were to run 2 logs, would the second one override the first one?
That's a very good question. So the question was, if you were to run 2 logs, would the second session overwrite the first one? The answer is no, it does not. Okay, so that means if you want to start from scratch and want to log from the beginning, there's a way to do it. The documentation tells you how to do it. I just cannot remember. But there's a way to reset the log so that it is cleared. Now you can always go to the file and delete it or rename it to something else. That always works. But if you don't do that, then all the logs will basically go to the same file over and over again. So you will see the log file getting longer and longer, because Logisim really does not know when you want to stop or reset the log file. Okay? So let's go ahead and see what happens at this point. Once you have everything set up, oh, this is also including the header line, which tells you which column is what. Okay? It can be handy, okay? But depending on the tool that you're using, it may or may not be necessary. So if you're visually going through the file yourself using an editor or something, yes, the header line is going to be helpful. But if you're using a tool to do it, it's not going to be useful. Okay? So I'll include it here. Close window. So from here on, everything that I do is going to be logged. Okay? So we'll go ahead and just run the program at full speed. So we take enable take. Now it's at a halt instruction. Okay, so we'll go ahead and stop simulation. Double check that it is actually at a halt instruction. You can tell that it is at a halt instruction because the output pin halt is going to be a 1. But the second question is, which halt instruction are we talking about? We have one halt instruction at 02. We have another halt instruction at 0A. Okay, so you can tell the difference quite easily by looking at the program counter. Then you go like, wait, the program counter doesn't make sense. It is not 02 and it is not 0A. What is going on here? Because it always auto increments after the fetch cycle. So that means the program counter reflects the location or the address that is 1 byte past the instruction that just got executed. So 03 makes sense because you have to subtract 1 from it to find out what was the last instruction that what was the address of the last instruction that executed. Okay? But our interest is not so much the program itself, because we knew that it would go to location 02 already. The question is, what does the log file look like? Okay? So now I switch to, let me just start a new terminal and go to that location. And we want to look at log.tsv and turn off spelling. There we go. That's really simple, right? All it shows is the first one is PC, okay, where the cursor is. That's P. So the PC goes from 00 to 01 to 02 to 03. Kind of makes sense. Yep.
If it stops executing at 2, why did it log 3?
Because remember, whenever one of the items that you list that you want to log changes, it creates a new entry. Yep. So that's why the last one, the last row, is when the program counter changes from 02 to 03. And that's before the halt pin becomes 1. Okay. And then register C never changes. Are we surprised that none of the registers got changed? I mean, this program doesn't do anything to change registers, right? So that's one way to do it. Okay. So now I'm going to go back to the simulator, and I go, okay, let's reset a few things, and then we'll go again. Now, all the things that I do now is going to trigger the log if I'm watching those things. So the first thing I'm going to do is I'm going to force the clock to go from a 1 back to a 0. If I click on the clock quote-unquote pin, it will change the state of the clock. Okay? Once you get to the hold instruction, you can clock all day long and nothing really changes. Okay? So this is not going to create a new entry in the log file. On the other hand, if I reset, click this particular reset button here to reset the processor, but keep the code in RAM, and I go like, okay, let's go at this again. Let's run it again. Okay, so we go to here, we go to ticks enabled, Control-K, and then we Control-K again to stop the ticks. Guess what? Now we have additional entries in the log file. So if I were to switch back to the log file and look at the file again, you can see it is now getting longer. It doesn't reset itself. So you have to watch out for this problem when you do the homework assignment, because the homework assignment wants you to count the number of times we get to a particular instruction for a particular case. So between the cases, you have to remember to reset everything. The best and the surest way to reset everything is to delete the file or rename it to something else. Now, in your homework assignment, because I want you to test out different conditional branch instructions, the best way is to rename the log file according to the instruction that you're testing. So you just change the log file name to jci.whatever log. Okay, the extension doesn't really matter. Okay, .txt is fine if you want to use Notepad to open it. Okay, is that okay? There is a way to reset the log file from so that it starts from the beginning again. If you go to User's Guide and you go to logging, and then you click on this one, you go to the File tab. I believe somewhere in here it talks about how to reset it. Okay. Oh, right here. If you want to return to the original one and want logging to continue, you will need to re-enable the log file logging manually using the button at top. In the middle of the indicator is what file is being logged to. If you select a pre-existing file, okay, so you have to reselect the file to start from the beginning. Even if it's the same file, by reselecting the file, it will ask you whether you want to overwrite. So it's right here. If you select a pre-existing file, Logisim will ask whether you want to overwrite the file or append to the end of that file. That is when you can control and go like, okay, I want to start from the beginning. Empty this file first, start from the beginning. Are we good so far? Yep.
Is the file that you have sequential, so the top grouping is the first run through and the next grouping is the second run through?
Say that one more time.
The file that you have, the one that we
Yes.
created, the first group,
Yeah.
the top is the original run, and the second group is the second run through?
Yes. So the question was, when we looked at the log file, whether the first 4 entries correspond to the first run of the program, and then the second 4 lines correspond to the second run of the program. The answer is yes, because it's just appending additional entries as we run the simulator. Yep.
Can't you get a line counter instead of them? So you can, even if you're appending, you can still see the difference between your logs.
Like that?
Yeah. Oh, wait. Never mind. I thought that every time it would append, it would
Okay.
change that.
So now that we have talked about this log mechanism, which is what you need to do your homework assignment, it suffices to do your homework assignment. But when you do further homework assignments, it gets more complicated, and doing it this way is going to be a headache, okay? So I provide a second method to do logging. It is not a part of your homework assignment, which means if you totally do not get how to do it in the second method, it's okay, okay? For this lab, you don't need it. But for other further labs down the line, for instance, when we try to implement the recursive version of Fibonacci, that is when you say, well, maybe the other method is better, okay? So I'm going to show you the other method, okay? So the other method is rather interesting, okay, because you have to do a little bit of work on the command line to get it to work, okay? But it's not too bad. It is not too bad. So the first thing you want to do is you close the GUI version of Logisim, because we are not going to use that. Instead, you go to the go to the command line. You say java-jar, and then wherever that the jar file is located, specify the path. Now, for those of you who are using Mac OS X or Windows, okay, you might be used to using the exe or having Logisim pre-installed. You will still need to download the jar file in this case to use this method. Okay, so this method is universal. Okay, it will work in Windows, it will work in Mac OS X, it will work in Linux, in every single command line of those particular operating systems. So it's universal, but it also means that you have to use the command line version of Logisim. You cannot just double click on the GUI one. Okay. So this is where you have to specify where that jar file is located. So mine is in Documents, CISP 310, logisim.jar. Okay? So depending on where yours is located, you might have a different path. And also remember, in Windows, you use backslash instead of forward slash. So all the slashes are now in the opposite direction if you were to use Windows. Okay? So this will normally just start up the Logisim itself. And then what you do next, I see a little bit of myself here, which annoys me. There we go. Now I'm not seeing myself. So now you have to specify some additional command lines, to do this. And obviously I have forgotten some of those. It's okay. That's why we have help files. Actually, I think I documented it somewhere. Oh, I remember. -tty, -tty table. Okay, that's the first switch you have to provide. What this means is don't start the program in GUI mode, start it up in TTY mode. Okay, TTY stands for teletype. Okay, now if I tell you what a teletype is, you guys would just laugh. It's a typewriter that has a serial connection to a mainframe computer. So it's not even a CRT, it's not even a screen. Things get displayed on a line-by-line basis, and it really is typed on paper. That is a terminal, okay? That's a teletype terminal. But all we need to know is it is not the screen, it's not GUI. Yep?
Is that -tty table one word?
No, there's a space in between. So -tty space and then table, and then space again. Now we have to specify the RAM content, and I have not, -load, that's it, okay? So when you specify -load, whatever follows is going to be loaded into the RAM component inside the design that you're loading. Oh, okay, that means I forgot one more important thing. Where is, oh, no, I got it, okay. I thought I forgot something, but I did not. So now you have to specify the RAM file. In this case, it is jci.csv. jci.csv, and I think that's it. Okay, let's give it a try. Because my memory is -tty requires a file name provided on command line. Right. Okay, so that's why. So I did forget something. I just did not remember what I forgot. There we go. Thank you. That makes sense. Okay, so this is almost the whole thing. Let me press the enter key first. If it works, then I'll go back and explain the whole thing. Yep, it does. Okay, so now I can go back and re-explain the command itself. So Java is how you get Java started. -jar blah 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 tells Java where is the Java archive file that contains the program that you want to run in Java. Okay, then we have processor 0003.circ. That is the Logisim file that we want to load into Logisim. Okay. Then we specify -tty table, which is telling Logisim, hey, we don't need the GUI version of this. We want to run this from the command line. Okay. Then we have -load /temp jci.csv, which tells Logisim if there's a RAM component in the design, this is what we want to load into the content of RAM. Okay, so we are basically stringing everything that we normally do by GUI, by pointing, clicking, and right-clicking and stuff like that onto one single command line. Okay, and then you look at the output, it's like, whoa, who can read this? I cannot. Because it's logging every single output pin there is in the design. Okay, how many output pins have we got in this particular design? Let me switch. Oh, I cannot because I did not start it in the non-GUI version. So if you want to start it in the non-GUI version, just kind of backspace all the way back to here. Okay. Everything that looks like this is an output pin, and there is a whole bunch of them. Okay. So, sorry? There are 8 shown so far, and there's a whole bunch right here. There's a whole bunch here, here, and here. And there's one more here. There's one more here. So there's a whole bunch. Huh? Well, we'll find out, okay? We'll find out. The way we're going to find out is, okay, this is silly, okay? We don't want to do it this way. We want to do it this way, except we're going to put a greater than here, and then I put it into temps.log.tsv. So the greater than symbol, this works across all 3 operating systems that I just mentioned. It works in Mac OS X, it works in Windows, it also works in Linux. It is called a redirection operator. All it does is to say, whatever was output onto the screen, now capture all of that into whatever file that I specify after the greater than. So now if I press the Enter key, it is as if nothing happens, because the entire output is put into the TSV file. I can double check that, okay? I can say vim/temp/log.tsv, press the Enter key, there it is, okay? Now, how is this any better than before? I can tell you it's not, okay? But, but when you go back to the shared folder, there is a spreadsheet that you probably want to make a copy of. It is called Log Analyzer, Trace Analyzer, there we go. It's called Trace Analyzer. Okay, so you double click that. I double click it. Now, this is where instructions are very important, okay? If you do not follow the instruction, it's not going to work. So I got to go back and change the ownership. Okay, now it's mine. Okay, very good. All right. So the first thing you want to do, okay, now you might want to bookmark this part of the video because you might have to refer to it from time to time, or you write down the instructions on a piece of paper. Whatever you do, okay, you probably need to go through this a few times to get used to it. The first thing you do is to go to File, but this time you want to import, okay? Do not open, do not overwrite, just import. When you import, you want to import from the file that I just created, okay? So most likely, okay, unless you have it uploaded onto your drive already, you probably want to go to Upload, okay? And then you specify the file. So we now go to /temp/log.tsv, press the Enter key, and you go like, oh, that's not too bad. Wait. Now you have options, and these you have to choose carefully, okay? Just like in one of the movies, I'm not going to name which movie. Huh?
He chose poorly.
Yes, he chose poorly. Yep. So now you, but I hope you guys would choose wisely.
I don't trust anybody in this room to choose wisely.
Okay, so you want to, when you specify import location, you want to replace current sheet, okay? You gotta pick this one correctly. If you say replace spreadsheet, you probably want to undo right away, okay? Because that's not what you want to do. You just want to replace current sheet, okay? So select that one. In the next one, you want to specify tab, okay? The auto may work first, may also work, but I always specify tab to be sure, okay? So you use tab as a separated type. And then the last one, you say no. Okay? The last one says convert text to numbers, dates, and formulas automatically. You want to say no. You go like, why not? Because the spreadsheet does not understand hexadecimal. When it sees something that has A, B, C, D, F, it will automatically think it is a text field and not a number field. And that will mess up a lot of things. So don't just say, do not convert anything, because my script will automatically do all the conversions for you. Okay? So after all of this, click Import Data. And depending on the speed of your computer, you might want to go get some coffee. Because it's not this part that takes long. It is the interpretation of all of this stuff here that takes a while. You can see the bar here. Even with my processor, which is not weak, okay, it's got an i7 processor, you know, kind of the mobile version of an i7, which is not too bad, okay? You know, it's not the fastest, but it's not bad at all. It still takes a little bit of time. Okay, now it's all done. So when it's all done, you go to the Analysis tab, and you go like, wow, it took you this long to tell me this much? Well, that's because the program doesn't do anything. All it is saying is we execute at location 0, and then we got to location 1, and then I forgot one thing that is super important when you use this tool. The first instruction has to be a no-op instruction. I forgot entirely, okay? So if you want to use this tool, okay, you have to go back and make sure that you have a no-op instruction to begin with. So I'm going to put a no-op here. Oh, okay, we can use this one. Go back to source. This has to do with a bug in Logisim, okay? So Logisim itself has a bug that's causing this problem to happen. So you have to start with a no-op instruction as the very first instruction. Then you can use JCI to when C is 1, and then put a halt instruction here. So basically, it's almost exactly the same program, except the first byte now is a no-op. So this time it will work correctly. If your log this way doesn't work, it's most likely because you did not have a no-op as the very, very first instruction. Okay? So now I have to re-download the RAM file, which doesn't take too long. So go here and download as CSV, save file to the same location, which is jci.csv, replace. Yep, there we go. Then we can go back and regenerate the log file. For those of you who know how to use a batch file in Windows or a shell bash file in both Linux and Mac OS X, if you don't feel like typing this much every single time, just make yourself a bash file. Okay? And you can learn how to parameterize the RAM file. If you don't want to learn even that, you can just say every single time I download from the spreadsheet, name it the same thing. Put it into the same place, name it exactly the same thing, then you can use the script without any changes every single time. Okay? So run it again, go back to the trace analyzer. And where is it? It's one of the spreadsheets. To the up, okay, right here. Huh, okay. So now we go back to sheet 1 and repeat that exercise. Go to File, go to Import, go to Upload again, specify the file, which is log.tsv, open it, and then make sure we select Replace Current Sheet, Tab, and No. Import data. Wait a little bit. You can see this one is longer. Okay, this is actually the correct trace. And because it's a spreadsheet, for any one of you who want to find out, okay, how does it get a job done? You're more than welcome to look at all the formulae in the spreadsheet. But don't download it as a spreadsheet file for Excel. Excel cannot do this, okay? A lot of the stuff that I do with Google Spreadsheet cannot be done in Excel. There we go. That makes more sense, right? Okay, so what is this doing? It is executing location 0. This is the no op instruction. Then it executes at location 0, 1. So column A is basically the program counter. It tells us where did we execute the instruction. Column B is telling us while we execute that instruction, what location did it read? Okay? So in this particular case, it did read location 02, except we didn't use it. Okay? We read it, we just go like, whatever. And then it also read location 03 because when we increment the program counter, that is when the data port of RAM changes, and that got logged. Okay? Did we write to any RAM location? Nothing. Did we change any register? Nothing. Did we change any flags? Nothing. And then we got to location 03 this time because we have to offset everything because I just added a new instruction. So when we get to location 03, that's when we executed the halt instruction, and that's why it was the last instruction to execute. So I know this looks like a lot of steps just to get something like this to work. But in your lab, okay, you're supposed to count a particular instruction at a particular location and how many times it has executed. This will help tremendously, okay? Now, one thing that you can also learn, okay, for those of you who say, can we count something really, really fast? There is a function called count, if. Look it up, okay? You will like it. So if you specify count if, okay, open paren, okay. Okay, you can click it. You can also, okay, I'll go ahead and look it up for you. So count if in Google spreadsheet. Okay, there we go. So you specify the range, okay? So the first parameter is a range of cells. You can select the entire column, okay? You can actually just click on the column header itself, in which case it will select the entire column. And then the second one is either a condition, like comparison, or if you want to look for equality, you just say what it is. So if you already know which address you're looking for, you can just type the address, and I think you still have to put it in double quotes because it's actually doing a string match in that case. But if you put in double quotes the location that you're looking for in the column, in the first column, it will come back with an answer and go like, yep, we stepped on this instruction 7 times, or 6 times, or 2 times, or whatnot. Okay, so, but you can now see why the spreadsheet is a really useful tool, because if I were to do this, okay, let me switch back to the spreadsheet first. So if I were to do my trace analyzer in a different way, where is it? This way. Okay, so if I were to use a customized program to generate the output here, then it would be more difficult for you to attach additional formulae to do the calculations or the analysis that you want to do. But because this is just a spreadsheet, okay, it's just a Google spreadsheet, if you want to exercise what you have learned about spreadsheets to automate some other task, to do some simple counting, to do some simple search and replace, not replace, but at least you can search, it's just a spreadsheet. Knock yourself out, do whatever you want. And this is Google spreadsheet, which also means you can add your own scripts if you want to do your own analysis of the output of your program. Okay? So this will come in handy later when we start to use the stack and use call and return and push parameters and pop parameters from the stack. Right now, is a good time to try to get used to it so that by the time we need to use it, the tool itself is no longer difficult to use. You already know what to do in order to make use of the tool. So are we good so far? So I think you got everything that you need to do tonight's lab. And as I promised everybody who asked, I am going to give you guys all the code, the access code to the lab right now. And I don't get any new comments. Okay, very good. So this is the new lab. And just like usual, I'll give you 1 week to work on this. Okay. So the passcode is JXI. So right here, that's our passcode, JXI. And I'll give you 1 week to work on it. Today is the 12th, so the 19th is the due date. And I'll even keep the same structure. This is also one more thing I want to go over before I end today's lecture. And we click Save and Publish. Okay, one person asked, can we log in from home? The answer is yes. Canvas does not care where you log in from. You know, the YouTube stuff obviously does not care. So one more thing, okay, one more thing before I end today's live stream / lecture is I'm gonna keep the same time slot, okay, for this class, because this was a face-to-face class. So that means you guys all have this time slot available. So I'm going to use exactly the same time, starting at 5:30, ending at 6:50 to do all the live stream. After which, I will also be monitoring, chat, channels. We can use the YouTube chat channel, but I think when I stop the chatting, the chat also stops. So we can use Canvas for the chatting. Or if you guys want, I can set up Slack or Discord, okay? But please do not tell me all of the above. That makes it kind of difficult because it's hard for me to kind of track, okay, here's Discord, nobody has asked any questions. This is Slack, okay, one person asks a question, and then the same question is asked by a different person on Discord. Then I have to copy and paste the answer, and then somebody pops up on YouTube and asks exactly the same question, then I have to copy and paste again. So whatever we do, we're going to stick with one particular way to do the online synchronous communication. So hopefully, I think Slack is okay, but Discord also has, which one has a free account that can do screen at least capture? Discord can do it, so we'll do it Discord, okay? I have a. Well, this class has 49 students. We just have to make sure there are no stragglers, like, oh, I want to join in your conversation. Somebody told me about this. I want to join in too. Okay, so I'm going to set up a Discord server for this class. So at the lab time, I'll be watching the Discord channel. So if you guys run into problems, take a screenshot, show me what you got, and then we can ask questions, answer questions, and stuff like that. So I'll be over at the lab today. Since I'm here already, might as well. Okay, but if you want to do this from home, that's fine too. I'm just going to stop the streaming at this point.